Hi there, my name is Siddhartha. Today we will share with you our findings on a new type of adversarial attack called the similar domain adversarial attack. Then we will talk about how to defend against such an attack using our proposed defense, Learn2Weight. As machine learning models are applied to more and more real-world tasks, addressing machine learning safety has become a pressing issue. It is already known that these models can be prone to adversarial attacks, where inputs are minimally perturbed such that it can render a targeted misclassification. Correspondingly, defenses have been proposed to improve robustness against adversarial samples. A question that has prompted this work is how well would NLP models perform against perturbations arising from different distributions? If an adversarial sample inserts perturbations from a target label to push its likelihood of being misclassified as that label, in other words label shift, and we also simultaneously insert perturbations arising from a different domain, in other words domain shift, would this attack be even more severe? Would existing defenses be able to block this attack? This is also actually a practical question. A black box attack already assumes an attacker may not have access to a target model or architecture, nor its training data, but what if the attacker does not even know the target domain? Motivated by these questions, we introduce the similar domain adversarial attack, where an attacker generates adversarial perturbations with respect to a domain that is similar to the target domain. First, the defender, the target of the attack, constructs a target model. An attacker, only having a rough idea about the target's task but lacking direct access to the target data or target model parameters, collects attack data from a similar domain and trains an attack model. They run the attack model on the test data to obtain correctly classified instances. They choose an adversarial attack algorithm and generate a set of adversarial samples. They expose those samples to the target model, hoping they mislead the target model to produce an output of their choice. We sample datasets from the Amazon multi-domain sentiment classification benchmark. We use an LSTM architecture by default and measure domain similarity with transfer loss and shared vocabulary metrics. We observe a significant gap between the original accuracy and after-attack accuracy, indicating that this attack can impose a valid threat to a target NLP system. Moreover, we observe a positive correlation between transfer loss and after-attack accuracy, and a negative correlation between shared vocab and after-attack accuracy as well. In this work, we are motivated to pursue a meta-learning approach to defend against adversarial inputs arising from different domain-shifted distributions. We hypothesized that an effective defense against the similar domain adversarial attack should adapt the target model weights with respect to the test time distribution of the input instance. First, we will introduce our Learn2Weight architecture and procedures. During training, Learn2Weight trains on sentences from different domains and a weight differential for each domain. We obtain the weight differential by finding the difference between the weights trained on sentence label pairs from a specific source domain and weights trained on sentence label pairs from the target domain. During inference, Learn2Weight recalculates the target model weights depending on the input. We consider the added constraint that the defender starts with only their own target domain and does not have access to a large pool of natural domains. We propose a method to generate a set of synthetic domains by iteratively inserting perturbations. To construct a perturbation set, we utilize an iterative minimax algorithm where we iteratively apply a maximizing adversarial perturbation factor and accept the batch of perturbed inputs if it yields a minimizing input distance. We repeat this t times. We use transfer loss as the distance metric to optimize for domain similarity and use FGSM as the adversarial attack algorithm. We evaluate our defense against various settings and configurations. Primarily, we find that Learn2Weight can outperform other baselines and ablations and achieve the highest after-defense accuracy. Though it performs the best, for our new attack setting, we also find that our baselines, including defensive distillation, adversarial training, and perturbation sets adversarial training, can all provide some level of robustness against a similar domain adversarial attack. All in all, to reiterate our contributions, we identify a new empirically effective similar domain adversarial attack where an adversary can choose a similar domain to the target task, build a substitute model, and thus produce adversarial examples to fool the target model. We also propose a defense, Learn2Weight, that learns to adapt the target model's weight using crafted adversarial examples. Compared with other adversarial defense strategies, Learn2Weight can improve the target model robustness against the similar domain attack. We also hope that our work inspires further work in machine learning safety. In particular, we recommend further study into robustifying models against cases of joint distribution shift, where test time shifts manifest simultaneously, such as domain shift and label shift in this case. Thank you for listening. We are grateful for your time. Please feel free to go for our paper and reach out if you have any questions.